Hey everyone, how's it going? Welcome back to another video. So today we'll be looking at this problem that is called unique binary search trees. So in this problem it says that you're given a value n and you need to tell how many structurally unique BSTs, binary search trees, can you make that store the values 1 through n. So you're given a value n, and you have to tell how many binary search trees are possible which contain all the nodes with values 1 through n. And they provided an example for you here where you're given the input 3. So it means you have the nodes valued from 1, 2, and 3. And you need to tell how many unique BSTs are possible that you can make from these 3 nodes. And as you see here, they've provided you with all the 5 examples, and the answer is 5 because there's 5 BSTs possible, right? So you have that answer now, and you need to devise an algorithm to get to this answer. And this obviously takes dynamic programming, but we'll see how we approach this problem and how we figure out how that we have to use dynamic programming in this, right? So before, rather than wasting a lot of time, let's just dive straight into it because this is going to be one long video. All right, so let's start off with the problem. Before going into and looking into how we'll find the number of unique binary search trees that are possible with n nodes, let's start off with a smaller number of nodes, and let's start off small and then we'll build up to n. So starting off, let's say that we have n equal to 0 nodes, which means we don't have any nodes right now. You could say that you only have a null pointer. So how many possibilities of building a binary search tree are there when you have a null pointer? Now you might think that you could say that there's no possibilities, but I like to think it in this way, that there is one possibility to build a BST which is rooted at a null pointer, something like this. So something like this is possible. So I like to say that there is one possibility when n is equal to 0, that is, you have a tree rooted at a null pointer. Let's say you have n equal to 1. Let's say you have been given a node, let's say that node is 10. And if that node is, and now you have only one node, how many how many binary search trees can you build with this one node? The answer is pretty simple, just one binary search tree with the root at 10 and no children. So the total number of possibilities when n equal to 1 becomes 1. So the number of unique binary search trees when you have either 0 or 1 nodes is just 1 in each case. Things become a little bit more interesting when you have, let's say, n is equal to 2. Let's say the nodes that you have now are 10 and 15. How many possible BSTs can you build with these nodes? Now you have like 2 options, and that becomes a little bit more interesting. You can have a BST rooted at the node 10, or you can have a BST rooted at the node 15. So exploring both these options, you'll get something like this. If the 10 is the root, then 15 will be its right subtree because this is a BST and larger elements appear to the left and smaller elements than the current node appear to the, the larger elements appear to the right and the smaller elements than the current node appear to the left. Similarly, if you root the tree at 15, 10 will appear on the left hand side because it is smaller than 15, and there will be nothing on the right hand side because there is no elements greater than 15. Now let's say we have n equal to 3, and let's say the 3 nodes that we have now are 1, 2, and 3. So now we have 3 possibilities for choosing the root node. The first one being a tree rooted at 1, a tree rooted at 2, and lastly a tree rooted at 3. So let's explore all of these possibilities. If we root the tree at 1, the left subtree will be empty because we'll have no elements that are smaller than 1. The right subtree at the same time will have 2 possibilities as the root node, which will be 2 and 3. You have to build a subtree made up of 2 nodes, 2 and 3. So we can expand this and we can explore all the options. For example, we can create a tree rooted at 2. If that is the case, then 3 will be its right subtree. If we decide to root the right subtree at node 3, we'll see that 2 comes out to be its left subchild. So these are the two possibilities when you root the BST at 1. So it comes out to be 2. If you root this BST at 2, at node 2, you see that the left subtree will have options to choose from 1, and the right subtree will have options as just one node, which will be 3. So there's only one option in each case. There's only one option in each case, which will be expanding this out to the only subtree that you can make with one node is the node itself, which will be 1, and the node itself and the right subtree as well, which will be 3. So if the tree is rooted at 2, the only option for the left and right subtree are the nodes itself, which gives us a total of 1 possibilities when we root at 2. Now, if you move further and we decide to root the tree at 3, if we do this, we see that the right subtree this time will consist of a null node because there is no element that is greater than 3 in our set. The right subtree at the same time will consist of, the left subtree will consist of 1 and 2, which means that we have to explore all the possibilities to build the left subtree using the nodes 1 and 2. So expanding this out, we'll get something like this. If we decide the root of the left subtree as 1, we'll get a tree that looks something like this. And if we decide to root this at 2, the left subtree at 2, we'll get a BST such as this, which is again a total of 2 possibilities. So adding these up, we get 2 plus 1 plus 2, which makes a total of 5 possibilities. So you can just write these out. You can write them as n equal to 0, n equal to 1, n equal to 2, and n equal to 3, where n basically defines the number of nodes, and we want to write the corresponding number of possible unique BSTs. So we have the numbers, we've already calculated that. For n equal to 0 we have 1, for n equal to 1 we have 1, for n equal to 2 we have 2, and for n equal to 3 we have 5, right? So we have these options with us. Now we can actually start converting this into a more formal definition. We just calculated all of these BSTs by hand, right? And now what we can do is we can start turning this into a more formal and a little bit more mathematical definition. But before we do that, we need to realize something. All the while we were finding the number of binary search trees possible for n equal to 3, we were doing some repeated work. What was the repeated work that we were doing? So let's look at this. When we knew that we have rooted the tree at node 1, we knew that the left subtree had 0 nodes to be built with, and the right subtree had the option to be built with 2 nodes. Similarly, when we rooted the binary search tree at 2, we knew that the left subtree had a total of 1 nodes, and the right subtree had a total of 1 nodes again. When we rooted the tree at 3, we knew that the left subtree had 2 nodes, and the right subtree had 0 nodes. So the total number of ways that were possible to find that, we basically went ahead and constructed the entire trees, right? We constructed all the possible trees with the 2 nodes and found that we can make 2 such BSTs. Then we went ahead and said that how many BSTs can we build with 1 node? How many BSTs can we build with this 1 node? And then we further went ahead and simply asked ourselves how many BSTs can we build with these 2 nodes? And we simply made these BSTs again. But if you look closely, we already calculated that answer. We already know how many unique BSTs you can build when you're given 2 nodes from the previous result, n equal to 2. We already know how many unique BSTs you can build when you have 1 node, which was 1. We already calculated that. So instead of calculating all of these answers again and again, what we could actually do was simply use the results from the previous answers. For instance, we know that the number of possibilities for the left subtree are 1. The number of possibilities for the right subtree are 2. So the total number of trees that you can build are 1 into 2, which is basically 2. And similarly, the number of possibilities in this case are 1 on each side, because you can build one unique BST when you have one single node with you, and you can build one unique BST when you have one single node with you. So you write 1 and 1, and the total number of possibilities will be the multiplication of these two, and this will be 1. Similarly, you have 3 here, and when you have 2 nodes to the left and 0 nodes to the right, we know that you can build a total of 2 unique BSTs with 2 nodes and 1 unique BST with 0 nodes, and this gives you a total of 2 nodes, which again gives you the same answer, right? Which is 5, right? So now let's move on further and see how we can write this in a more mathematical way and in a more formal definition. So now we'll define two functions, one of them being g of n. Now g of n defines the total number of structurally unique BSTs possible given n distinct nodes. So g of n is basically the values that we just calculated. G of 0 will be 1, g of 1 will be 1, g of 2 will be 2, and g of 3 will be 5. We further want to break this function down. We further want to break this g of n function down. So we use a new function which is f of I comma n. F of in basically means the total number of structurally unique BSTs rooted at I given n distinct nodes. So if we look at the previous example, we see that f of 1 of 3 would be basically this entire structure, the total number of trees possible, unique BSTs possible with 3 nodes rooted at the first node. Then we have f of 2 comma 3, which is the total number of BSTs possible rooted at the second node, which came out to be 1. And similarly, if we write f of 3, we can say that this is equal to the total number of BSTs possible rooted at the third node when you are given 3 nodes, and that turned out to be 5. And if we look at this, we can simply add all of these up. And get the answer for g of 3. As we did in the previous example, when we added each of these values up, we got 5, which was basically this value that was there for g of n. Now this might seem a little bit confusing, but just stay with me here. And it takes a little bit of time to understand the concept completely, so just give this like a few more minutes. So we had this here, and we simply wrote this like f of 1 of 3 rooted at 1, 2 options for the right subtree, which are 2 comma 3, and no options for the left subtree. Then you have the tree rooted at 2, 1 option for the left subtree and 1 option for the right subtree, and the tree rooted at 3, 2 options for the left subtree and no options for the right subtree, right? This was what we made. Now, can we convert these values? Can we convert this function? Can we break this function down even further in terms of g again? So this can be written as g of 0, the total number of possibilities when you have 0 nodes. The total number of possibilities when you have 2 nodes will be g of 2. Then the total number of possibilities when you have 1 node will be g of 1. And when you have 1 node again, you write g of 1. And then you have 2 nodes here, you will write g of 2. And you have 0 nodes here in the end, and you will write g of 0. And you'll multiply these to get your answers. Now, you can see that you can relate this value of g, and you can actually know which all previously found g's you actually want to use. G of 0 is basically g of I minus 1, and you can write this as g of n minus I. So what does this mean? This kind of means that you're finding the number of elements left on the left subtree. How many elements are left? You start off at element number 1 and you go on till the root. So the root is the ith element. So the number of elements to the left will be all the elements smaller than this, which will be I minus 1. then you have all the elements that are greater than this current root, which will be all the numbers after this current node, which will, for example, here will be 2 and 3. So you write something like n minus I, which will be 3 minus 1. So this gives you 2. So you write 2 here. When you're at node 2 as the root, you simply write g of 1, which is g of I minus 1, and I here is 2. So you write g of 2 minus 1, and you get 1 because there's one element that is smaller than 2. Similarly, when you're finding for g for the right subtree, you write g of 1 again because the number of total number of elements minus the current index, you get all the elements to the right of the current index, which is 1, which is 3 minus 2, and you get 1. And again here as well, you get I minus 1, which is 3 minus 1, and you get 2, which is the number of elements left to the left of the current root, and the number of elements to the right will be again 0, which is g of 3 minus 3, right? So yeah, that is basically how you will correlate these. And for each of the indices, for each I, you'll calculate g of I minus 1 multiplied by g of n minus I. If I went too fast in this portion, and if you felt like this was a little bit too fast for you, just scroll back and just look at this sequence again. It's not that difficult, and if there's still any worries or if you still don't understand, just move ahead to the coding part and we'll make this stuff clear at that point, right? So this is basically all you need to know on how to divide this problem into sub-problems, and we'll continue ahead in the coding section. Alright, so here we are back in the code editor, and the first thing that we need to do is create a vector or an array that will keep track of all our previous answers, or for all the previous values of g, which is basically the g of n, which is basically the number of unique BSTs at each of the intermediate n values. So we start off at 0. So we will be creating an integer vector, which is basically an array. I'll call it g. The size will be n plus 1 because there's n plus 1 elements, because we start off at 0 and move on till n. So 0 to n makes it n plus 1, and we'll initialize all the values with 0. And we already know that we initialize g of 0 as 1 because when you have no nodes, we say that the tree is rooted at 1. So we say that there's one possibility for g of 0. And if we are given one node for g of 1, we'll say that there's again another one possibility, because that BST for g of 1 will basically be the tree itself, as we discussed in the algorithm before. So we'll just initialize g of 0 as 1 and g of 1 as 1 as well. Now what you'll do is you'll start off your iteration for your entire loop, that you loop through each of the values of n of I till you reach n. So from 0 to 1, 2, 3, 4, 5, 6 until n, you'll find all the intermediate answers, and then later you'll use those answers to build up your result for g of n. So we've already written the values for 0 and 1, so we'll start off at int I equal to 2, while I is smaller than equal to n and plus plus I. Now you are at, for example, currently you are at I equal to 2. So you are looking at n equal to 2, and you have two possible nodes, that is, let's say node 1 and node 2. So now, as we looked at the example in the previous slides and the previous on the whiteboard, we saw that for g of 2, you would divide this into and break this down into functions of f. So g of 2 is equal to f of 1 comma 2 plus f of 2 comma 2. I'll just write that down here for a little bit better explanation. So g of 2 is equal to f of 1 comma 2 plus f of 2 comma 2, which basically means that f of 1 comma 2 means the number of binary trees that are BSTs that are possible when the tree is rooted at 1 and the total number of nodes are 2, and f of 2 means that the number of BSTs possible when the tree is rooted at 2 and the total number of nodes are also 2, right? So for that, we need to iterate over each of these root nodes, each of these possible root nodes. So we'll start off at for int j equal to 1 from the first node till we reach I, which will be the current n. So we start off at 1 and we move on till 2 in this case, plus plus j, and we calculate the value of g based on each of these values, right? So we already discussed that f of 1 comma 2, we can break this down further as well. For example, f of 1 comma 2, I told you that this will be equal to g of I minus 1, right, multiplied by g of I minus j. I'm sorry, this will be j minus 1, right? This will be the current node minus 1, which will mean the number of elements to the left, and g of I minus j will be the current value of g that we are iterating over. For example, the current n, for example, we're looking at 2 nodes right now, so total number of nodes minus the current index or the current root that we are considering. So this will be the elements to the right, and this will be the elements to the left, and the g values will simply tell you how many BSTs you can make with those number of elements. So and when you multiply that, you get the total number of possibilities for that current value of f, which will be the number of BSTs rooted at your current root, which is, for in this case, 1. And we'll just write this as g of I plus equal to g of j minus 1 multiplied by g of I minus j. And this should be it, and we'll return the g of n, and that should basically give us our answer. So we'll try running this. Let's see how it goes. We get the correct answer. We'll submit this, and we get 100% faster result, 0 milliseconds, and a nice memory usage as well. So this is how you solve this question. It took quite a bit of time to record this. I re-recorded this video, I think, at least 20 times because I wasn't able to get a satisfactory whiteboard explanation. But here it is, and I hope you understood this question well. I'll try to put some links down below as well to some other channels. Back to Back Sui has an amazing video on this, and Tushar Roy's channel also has an amazing video on this. The reason I made this video here was because I kind of felt that both of those videos provided something new and provided something nice, and I really wanted to bring in together the coding and the whiteboard part. And there were some things that I felt were not as clearly explained in both of those videos, so I tried to cover that as well. And just tell me what you think of this entire video in the comments below. If you like this video, hit the like button, and if you want to see more content, just subscribe to the channel, and I'll see you in the next one.